Yes. Okay. People are easy, not sure about the answer keys. Yeah, that's what I heard. That the answer keys are. Yeah. Never mind. Okay. So yeah. So the main agenda today is to talk about trees, and in particular talk about spanning trees of graphs and problems that use it. And we'll also see special kinds of spanning trees of graphs and problems related to that. Okay, so before that, I just want to know if everyone knows what paths, trails, and walks are. So I'm just mentioning that. So a path is simply uh, something of this sort. V1. Uh, okay. Uh, Often people don't put the edge, but let me put it for now. So this is how a path looks like, where E1 is an edge that connects V1 and V2. We'll assume that our graph is simple. Yeah. And so a path is finite, by the way. We assume that paths are finite. In fact, we also assume that our graphs are all finite, and between any two vertices, there's at most one edge, and there are no edges from a vertex to itself. So that's what simple finite graph means. And a path is of this form where no two vertices are equal to each other. So you cannot repeat a vertex. So think about yourself traveling on the vertices. Yeah. So and the edges being roads between the vertices. So yeah, you cannot go back to the same city. On the other hand, a trail is very similar, but instead we're allowed to repeat cities, but not roads. So EI is not equal to EJ. So if a graph is something of this form, and if we start from here, uh, actually, if we start from here, then this is not a path because the vertex circled has been repeated twice, but it is a trail because no edge has been repeated. Yeah, okay. And finally, we have something called a walk, which is even more general, that we can repeat edges as well as vertices. So every path is a trail and every trail is a walk. There is a trail which is not a path, just demonstrated, and there is a walk which is not a trail. Um, so simply doing this, for example, right? This is a walk, but we repeated the edges. Okay, and one of these is easy to count in a general graph. Can you tell me which of these is very obvious to count in a graph? How many of these there are in any graph? So think about the number of walks in a graph. How many are there?
Infinite?
Except for one case, when? So
All
what if the graph
vertices are
has,
isolated.
yes. And so how many walks are there in that graph?
The number of isolated points?
Exactly.
Isolated vertices.
Yeah, exactly. So if a graph has any one edge, then that graph can have infinitely many walks because for any natural number n, I can just take n steps along this edge. So there are infinitely many walks, even if there's a single edge. But if there are no edges, so we have a graph on n vertices, which are all isolated, then there are only n walks because simply V1 itself is a walk. That is, we start at a city, but we don't go anywhere. That counts as a walk. So we have only n walks. So it's either in the number of vertices or infinite, depending on how many edges there are. Okay. So
So
that wasn't too
even if there is
complicated.
one edge, like n minus one
Yeah,
vertices are isolated and the other two are not, then also they are infinite, right?
yeah, because as long as there is one edge in the graph, I can simply make walks using only that edge. So if the edge joins A and B, then I have the walks A, AB, ABA, AB, 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 ABA, etc. Right? So there are infinitely many of them. And the number of paths is not so obvious. So there are efficient algorithms to compute the number of paths, but there are no direct formula as such. Okay, not our concern really. Also, I missed writing what a cycle is. I'll just write
Are
it
there
here.
efficient algorithms for trails?
Actually have to think. I'm not 100% sure. I'll think about it and tell you. So, uh, in fact, actually, efficient algorithms for paths is also not obvious. So what I mentioned is not true before. Uh, ac- in fact, now I think there might not be efficient algorithms for them. I'll think about it. I actually think that so I said that paths have efficient algorithms, but now I think that's not the case. Uh, I'll think about it and definitely tell you this. It shouldn't be very hard. I don't want to spend time right now. Okay. Uh, because I think we can relate it to finding Hamiltonian paths in cycles and graphs, which is known to be no, which we think does not have efficient algorithms. I'll let you know. Yeah. Okay. And I just wanted to mention what a cycle is. And so a cycle is similar to a path, but we simply close it. So we have vertices v1, v2 up to vn with the edges joining them and back to v1 where we have vi not equal to vj for all I not equal to j. So something like, well, this n is not the same as the number of vertices, it's just some general n. v3 up to vn and then back. So it's simply a cycle, right? And so we can also generalize cycles to closed trails where we come back to the same vertex, but we don't repeat an edge, and also like a walk where we can use the same edges and vertices and we come back to the same vertex. So you can generalize it to closed trails, closed walks. Also called clouds. Okay. And our main topic for today is trees. So a tree is simply a graph which is connected and acyclic. So what that means is that so notice this graph that I've drawn here. So there are no cycles in the graph, but it is connected, which means from any point to any other we can travel through the graph, right? So it is a tree. And note that the number of edges in a tree is always one less than the number of vertices, no matter what the tree is. So the average degree would be 2m by n, because the sum of all degrees equals to twice the number of edges. So 2m by n, which is 2 minus 2 over n, which is less than 2. So the average degree of a tree is very small. If an edge is deleted, how many connected components are there? So if I delete, say, this edge, then it splits it into two connected components, right? And if I would have deleted this edge, then that also splits into two connected components. In fact, no matter what edge I delete, oops, sorry. In fact, no matter what edge I delete, say this, consider the endpoints of it, and then the points that can be reached to the points that we can reach here and the points we can reach here, right? Without using this edge that sort of forms the two connected components. So these are the set of all points that can be reached to U without using the edge UV, and these are the points that can be reached by or to, it doesn't matter, V without using the edge UV. And so these are our connected components. And so it'll always be 2, no matter what edge we delete. Okay. And what happens if we delete a vertex? How many connected components do we get?
3 if it's like not an end vertex.
Let's see.
Whatever the
Suppose I
degree of the
delete-
vertex was.
Yes. Yeah. Suppose I would have deleted this vertex, then I get 4 connected components. Right. So in fact, if we delete a vertex, then notice that notice what happens. So each edge deletion individually forms a new connected component in some way, right? So that is to say, so let's just do it one by one. So suppose I wanted to delete this vertex. So instead what I do is I delete this edge first. So now I have 2 connected components. And then I delete this edge. So now I have 3 connected components, then this edge, and then this edge. So I have 5 connected components. But then I have to delete this vertex itself. So that reduces the number of connected components by 1. So 4 connected components. Right. So in general, for any vertex of degree D, so actually for any vertex V, if its degree is degree of V, deleting the edges one by one increases the number of components by degree of V. But then deleting that vertex subtracts the number of connected components by 1. So the answer is degree of V. Yeah, so there are so many questions that we can pose. In fact, try to pose your own questions and answer them. So you can do that. And we finally come to talk about what a spanning tree is. Okay. So consider any graph which is connected. I'm just drawing some arbitrary graph. Okay. Yeah. And notice that in such a graph, there will exist a subtree which has, so if the number of vertices in this is n, there will exist a subtree in this graph which uses all n vertices. So of course this is a tree, right? Only using these 2 vertices and this edge. But this is not the kind of tree that I want. I want a tree that uses all vertices. Let me use a different color. It's a little, yeah. So for example, so can someone tell me a tree in this? Let me label the vertices. 1, 2, 3, 4. So give me a tree in this that goes through each vertex.
Oh, 4, 3, 3, 10,
Okay.
3, 10, 10,
Yeah.
9,
Okay.
9, 8,
Okay.
8, 7, 3, 2, 2, 1, 1, 5, 5, 6.
Good. Let me do 6 times just to mix it up. Yeah. Yeah. So this is a tree, right? That goes through each vertex. So this is what a spanning tree means. There's another solution, 4, 3, 2, 1. Okay. 4, 3, 2, 1, 5, 7, 8, 9, and then join to 10, 6. Yes. Yeah, so there's a long path. And yes. And notice that the way to find a spanning tree is actually quite simple. So we just keep adding edges as long as it doesn't form a cycle. So so essentially we pick any edge, and then we pick any edge joining 3, or in fact any edge in the graph is okay, but we pick this edge, and then say we pick this edge, and then suppose we pick this edge, and now in the next iteration we'll be careful to not pick 9 and 3. The best way to do that is to always pick a new edge and join something to the edge, to pick a new vertex and join it to a vertex that has already been picked. So we only consider vertices other than 2, 3, 4, 9, 10, for example 8, and then try to see if it is a neighbor of one of the vertices that we've already picked. So 8 is a neighbor of 9, so we can join it. And then let's say we pick 5. 5 is not a neighbor of any of these vertices, so let's leave it for now. Let's pick 1. 1 is a neighbor of 2, so we join it. 5 is a neighbor of 1, we join it. 6 is a neighbor of 5, we join it. 7 is a neighbor of 5, we join it. Right, so this is also another tree. So we simply just pick vertices. We pick a vertex outside the list of vertices we've already picked, and we join. And if it connects to one of the vertices we've already picked, then we join it to any one of them. And we can always do this because the graph is connected. So at any point, if we arrive at some vertices such that it is impossible to find a vertex that connects to one of these, then say 1, 5, 6, and 7, and none of these connect to any of the vertices here, then this is a connected component of its own, and there is no edge here. That's a contradiction to our assumption that the graph is connected. So, yeah, so let me erase this. So, for any G on n vertices, a spanning tree of G is a subgraph H of G such that one H is a tree. Generally, we'll use the letter T for a spanning tree, but I'll just use H. And H has n vertices. Yeah. So it spans the vertices of the graph, hence the term spanning tree. Okay. So let's try a problem. Let me not do this now. Let me.
Oh, shouldn't
let
H have
me-
n
let
minus
me-
1 vertices? A tree has
No, it has
minus
n
1.
No, it has n minus 1 edges. So the number of vertices is n.
Okay, n vertices.
Yeah. Okay, so we tried this problem. So we have a connected graph on n more than equal to 3 vertices, such that if we delete any cycle, then the graph is not connected anymore. So what's the maximum number of edges in G? If you need clarifications of the problem, please ask.
By deleting a cycle, do you mean do you even delete the vertices, or just the edges?
Yeah, that's a good. Yeah, the edges of the cycle. Uh, yes, the edges of any cycle. Then the graph is not connected. So what's the maximum number of edges in G? Uh, I see what you mean. Okay, I'll wait for more people to sound it. We have two answers in the chat so far. So what do we need in order to guarantee that a graph is connected? It suffices for it to have a spanning subtree, right? Because if it has a subgraph that spans the entire vertices, then that tree itself sort of connects the graph, and then more edges don't really matter, right? So, so for any set of vertices, as long as there is a tree going through them, no matter what more edges there are, this graph is definitely connected because it's already connected through these trees. So one idea is that if you can find a spanning tree in G and you can delete a cycle that doesn't use any of the edges from that spanning tree, then the graph remains connected. That is say I have a spanning tree on spanning tree of this sort, and then I have a cycle of this sort, say this, this, and this. Then I can delete the edges of this cycle and the graph will still remain connected because that spanning tree in the white color still remains after deleting this red cycle. So that's one idea. Let me keep that diagram. Uh, so what does it mean that G has a spanning tree and then it has a cycle outside the spanning tree? What does that imply?
If it has a cycle outside, then we can just delete it, which is a
Yes, exactly.
contradiction.
Exactly, right. So suppose G has this tree and there are cycles outside the tree. then if there's any cycle outside that doesn't use any of the edges of the tree, for example, this, then I can delete this and the graph is still connected, which contradicts our hypothesis, right? Because we assume that deleting any cycle makes the graph disconnected. So it cannot have any cycles outside the spanning tree, right? So that is to say that, so consider a spanning tree T of G if the edges of outside ET, so EG minus ET, form some cycle C, then deleting the edges of C keeps G connected. And that's because no edge of the spanning tree has been deleted, right? So since a spanning tree is enough to keep the graph connected, the graph still remains connected. So this is a contradiction, right? So what does that mean? That the edges outside the spanning tree has no cycles. This means edges outside, okay, let me not say outside, in do not form a cycle. And so what does that imply? So how many edges can there be in this?
At most n-1.
Yes. So since there is no cycle being formed, so I don't think I mentioned this property before, but a tree is like a maximum, sort of a maximum, not just maximum. Okay, it's also maximal. Yeah, okay. So it's sort of the largest number of edges that we can get in a graph without forming a cycle. So if the number of edges is n or more, then there will always be a cycle in the graph. And so since these edges EG minus ET do not form a cycle, there are at most n minus 1 edges here. And note that E of t itself has exactly n minus 1 edges, right? Therefore, the number of edges in G can be at most 2 times n minus 2, which is the sum of these. But this is not enough because we still need to show that this can be achieved, because the question asks for maximum, which means that there should be a graph with 2 times n minus 2 vertices that such that deleting any cycle causes the graph to be disconnected. So yeah. Can we find lower bounds? Can you construct a graph on?
I found for 2n-3, but for all cases 2n-2 is failing till now at least.
Okay, so can you tell me your construction for 2n minus 3?
Consider a star.
Okay.
First, and we now ignore the center vertex, and for the outside vertices we consider any tree. Like draw anything outside, which is a tree.
Yes. Okay.
Now,
Yeah.
if
So Yeah, this works. So let me draw it better. Uh, so let's say we have 7 vertices. We make one of them center and join everything to the others, and then we make a path on the outside. So this has 2n minus 3 uh, edges. So you can generalize this, right? We put something in the center and make n minus 1 edges, and then make a path of length n minus 2 outside. So that's 2n minus 3 edges. And deleting any cycle in this actually disconnects the graph. Yes. Why is that so?
Does it disconnect? Like you can find a cycle here that doesn't, for example.
Oh, yeah, it doesn't. Yeah, you're right. Because this, for example, yeah, you're right. So this construction doesn't work. Uh, okay, let's think of some other construction. Maybe this works. How about this? So it's like the same construction, but we specialize the tree. Maybe there are n minus 2 vertices here, 2 here. We join everything here, join everything here, and join this. This is also 2n minus 3 edges. Uh, yeah, but the same problem. No, this is different. Yeah, this works. Yeah, okay. Yeah, this construction works. So these are 2n minus 3 edges. And this works because any cycle has at least 3 vertices. So any cycle in this will use one of the vertices on the right because there are only 2 vertices on the left. But the degree of this is 2, right? So any cycle through this will delete both edges through it. Right? So that will make this isolated. So this construction works. So it's same as Arjun's construction, but instead so I took the a path through the outer vertices. We take a star on the outer vertices. So that's exactly what his construction is. Specialize the outer tree. Okay. Yeah. So 2n minus. So we have that the answer so far is at least 2n minus 3 because we found a graph satisfying the hypothesis and we were asked to find the maximum, right? So we found a graph on 2n minus 3 vertices. So the answer is at least 2n minus 3 and it's also at most 2n minus 2 because of what we discussed here. Yeah, but which one is it? So I'll tell you that the same formula works for all n. So that should give you the answer. For n equal to 3, the answer cannot possibly be 2n minus 2 because that's 4. And a graph on 3 vertices cannot have 4 edges. So, yeah, so the answer is actually 2n minus 3. So we have to improve this actually. Instead of finding a better construction, we need to improve our argument. Improve argument. ideas? Oh,
Can we show that the two trees must share a leaf?
Um, two trees must share a leaf.
Because then we have a vertex of degree 2 delete and induct.
I think it's not true. We can consider a graph on 4 vertices and divide it into 2 trees, and leaves would be different if we do it correctly.
Yeah, fine.
Yeah, I see. Okay, so this is one idea. So we have G, and we took a spanning tree of G, right? And then we said that the remaining edges themselves do not form a cycle, right? So suppose the answer were 2n minus 2, right? Suppose the answer were 2n minus 2, that is, there is such a graph. And so the remaining, so if we delete these white edges, then we remain with n minus 1 edges that form an acyclic subgraph of G. And so they also form a spanning tree. So basically G is a union of two spanning trees, disjoint. So we have something like this. Just trying to come up with something that doesn't repeat edges. Okay, I'm just drawing a path. Okay, this. No. Uh, okay, let's do this. Yeah. So it should be of this form, right? So red and forms a spanning tree. The white edges also form a spanning tree. Unfortunately, in this there are cycles that can be deleted uh, to keep the graph connected. There are quite simple such. I think this works, for example. So the idea is, can we choose our white spanning tree P more carefully? So let me go back to the analysis that we had before. We picked any spanning tree T and said that the edges of the graph, other than the edges in the spanning tree, cannot form a cycle. And so there are at most n minus 1 edges there, and there are exactly n minus 1 edges in the tree. So the graph is at most 2n minus 2 edges. But can we now take a special T that improves this analysis?
Yeah, I think we can. If there is a tree which disconnects the graph, like if we're removing it, then we are done.
Exactly. Right. So in fact, can we find a tree T such that removing the edges of T disconnects the graph.
If this is not true, then each vertex has degree at least 2.
Sure, yes. So the point is that if we can find such a t, then what happens is that if we consider the edges EG minus ET, then the edges still form an acyclic graph, but it can no longer be a tree because it's disconnected, because these edges form a disconnected subgraph of G, and so it is disconnected. And this has at most n minus 2 edges, in fact, because if you have n minus 1 edges in an acyclic graph, then it will necessarily be a tree. So that is any 2 of, so this is, I'll write it in blue, any 2 of acyclic n minus 1 edges and connected implies tree. So it is
Can you
impossible
tell-
for a graph to have, sorry?
Can you please tell again that how there's two spanning trees cannot exist? I couldn't get that.
Yeah. So I'm telling you that, yeah. So for that, So if we remove the edges of T and such that the graph is disconnected, then notice that the edges of EG minus ET form an acyclic and disconnected graph, and so it has at most n minus 2 edges because of this star. So then the graph will have 2n minus 3 edges. We've still not found such a T, so I've not said anything about that so far.
But doesn't such a T like trivially exist? Like pick a vertex, add its neighbors, and
Exactly. Yeah, that's all. Pranav, you're out.
Why should it be disconnected, the other part, after removing T?
I'm sorry, what was that?
Why should it be disconnected? Oh wait, T is a cycle which we
T
are
is a
removing.
tree. No, T is a tree.
Okay,
The
so why
point is
should it
that
be disconnected?
it shouldn't be. We're asking if there exists such a tree for which removing the edges of T disconnects G. So
Okay.
can we find such a tree? The idea is that if we can find such a tree, so remember that if the answer were 2n minus 2, then the edges of the graph formed by removing a spanning tree T itself forms another spanning tree T prime. But we want to sort of disprove that such a thing is possible. So I'm saying that since any such tree, a tree is necessarily acyclic and connected, can we somehow force T prime to not be connected so that it doesn't form a spanning tree? So that's the idea. Because we cannot really do anything about the acyclic thing. So maybe something about the disconnected thing can be done. Right? So yeah, so it suffices to find a tree such that removing the edges of T disconnects the graph G. And actually such a tree trivially exists. So why such a tree exists is the following. Remember how we found spanning trees in the beginning? So remember that the idea was that we sort of just pick any vertex that joins any previously picked vertex, and we just include it at that edge, right? So one way of doing that could also have been to pick any vertex 8 and pick all its neighbors. So this is also allowed, right? 8, 7, 9, 5, and then pick 9 and put all its neighbors that were not already in the graph. So 2, 10, 6, for example, and then pick any new vertex and put all its neighbors. Say I pick 2 and put 3 and 1, and then I pick 3 and put 4. So I can do this sort of a thing where I just pick any vertex and put all its neighbors in the and the edges corresponding to it, as long as the vertex that the neighbor vertex is something new. So yeah, okay. So how does that help? The point is that okay. So the solution is that pick a t such that okay. So fix a vertex v pick a tree or pick a spanning tree T that uses all edges incident on V. And why can we do this? We can do this because of the procedure we mentioned before. Spanning trees are very easy to create, and there are so many ways of doing that. The idea here is that when we making the spanning tree T, we take V and we put all its neighbors in the tree along with these edges immediately. Since this doesn't contradict anything because there are no cycles formed so far, we can so for the remaining vertices we can do what we did before, that if there is any edge between this component and here, we include that edge and the vertex. So for example, if this is an edge, then we include it, and then if this is an edge we included, this is an edge we included, this not this, sorry, this and this, right? So we still have a spanning tree, but the added bonus is that this vertex has all its neighbors, in fact, all these edges in the spanning tree, right? And so now if we delete the edges of T, then V becomes isolated. So now E of T is acyclic, as we discussed before. We cannot have a cycle outside the spanning tree because deleting that cycle will keep the graph connected, contradicting the hypothesis. So these edges form an acyclic subgraph, and so by this I actually mean the graph formed by using these edges, not the edges themselves. And this is disconnected because V is isolated in it, in the complement graph. That is, if we delete all these blue, actually are white spanning tree, but I've drawn it blue here, then it's disconnected. So this is at most n minus 2, and we said that this is n minus 1, and that implies the result, that the answer is at most 2n minus 3. I hope that made sense. Questions?
No doubts.
More doubt?
Can you scroll a bit up for a second?
Yes. More?
No, it's fine.
Okay.
Yeah, it's fine.
Okay. So remember what we did here, that we said, just to revise the solution once more. So for any spanning tree T, if we delete the edges of the spanning tree, then the remaining edges in G cannot form a cycle because that will directly contradict the hypothesis. And so these remaining edges can be at most n minus 1 in number, and the tree itself has n minus 1 edges. So the graph has at most twice of n minus 1, which is 2n minus 2 edges. But so we sort of skip the time over it, but if you try to construct for 2n minus 2, you'll probably keep failing, and 2n minus 3 is easier to construct. And so that sort of recommends that the answer might be 2n minus 3 and not 2n minus 2. And yeah, and so we improve our analysis that we have the same proof, but we choose the t to be better. So we chose t such that these edges in this not only do not form a cycle, but it also forms a disconnected graph. So we chose a t, and how we did that is by picking a vertex v and then picking all its neighbors and picking all the edges incident on that vertex, and we put it in t, and we can do that. And that allowed the edges of the graph outside the spanning tree to not have any edge incident on V. So then the graph is disconnected. That is, the edges other than the edges of the spanning tree do not connect the entire graph, and retains the acyclicity property. Right? So this do not form a cycle is still true. And so these can be at most n minus 2 in number now, and not just n minus 1. And so the answer is 2n minus 3. Yeah, and then we had this construction for 2n minus 3, where we form these edges between 2 and n minus 2, and we also form this edge. Okay. Great. Let's do this. This has some instructive value. So okay, maybe before that I should actually tell you what these mean. Okay. So we talk about some special graphs called special spanning trees called BFS spanning trees, and let me not use the word spanning tree for these. So let's talk about BFS. What this stands for is actually breadth first search. First search. Okay. So we have any such graph G. Okay, I think this should be fine. That's a lot of edges. Yeah. And this is a special sort of a spanning tree in the graph. We assume it's connected. And what we do here is the following. We sort of make levels on the graph. So we start with the vertex V, and then we join all vertices to, okay, so let me describe this procedure like this. We connect to V all its neighbors, right? So let me not label the vertices. And then in the next step, we consider all neighbors of neighbors. So that would be these. Neighbors of neighbors other than the ones we've already seen. So technically W is a neighbor of a neighbor because V, U, W, but okay. And then we join it to the neighbors, right? And then we see neighbors of neighbors of neighbors. We join it to one of the parents, right? Not both. The idea here is that, note that these are at a distance of 1 from V. This itself is the distance of 0 from V. These are at a distance of 1 from V. These are at distances 2 from V. These are at distance 3 from V. right? And hence it's called breadth. It's like it's like picking a vertex and then looking at everything around V, which um, which connects to it, and then looking at everything around those neighbors that connect to it, etc. So, yeah, I hope there's some intuition as to why it's called breadth. Yeah, so I hope the procedure was clear. And note that this tree will differ depending on some choices, right? So, for example, consider this vertex, or not that, maybe this vertex. I could have joined it to the other parent, so I could have joined it to this instead of the one on top. But yeah, I did not do that. Or it could also depend on the choice of V, right? So if we start from some other vertex, then the tree would look different. But it's fine. Yeah. So the interesting thing about this sort of a spanning tree is actually the edges that are not in the tree. And so that's actually the more interesting part. So let me just draw any such tree, which is actually formed by performing. So this procedure that I did was actually called a breadth first search. So it's like, so think of it as a search problem where you're at a city V and you want to search for a friend of yours that's at some city, I don't know, W. And so what you do is a breadth first search. That is, you first search all cities joining V, and then you search all cities joining the cities that join V, etc. So that's the idea. You don't go deep into, so you don't first go from V to W to U to T and then come back to something else, etc. So that's not what we do here. We instead go through like breadths in some way. Yeah. Okay. And hence it's called a search problem. So, but okay, we don't need to be concerned about that. Okay. Uh, so suppose we have any such search tree. Let me draw a little more edges. Okay, I think this is enough. This is that, and this vertex V is often called the root of the tree. So this is also called the root, and these are called leaves. So I know it sort of looks reverse, but if you sort of tilt it, then it makes sense why they're called root and leaves, even though here the leaves are at the bottom and the roots at the top. Okay. Yeah, so note that these are at distance exactly 0 from V in the original graph, not just in this tree, but in the graph itself. So these are at level 1 or distance 1, 2, 3, and then let me draw them at the same height so that it's easier to see. And so these are at distance 4. All these. So what can we say about the other edges of the graph? So for example, can I have an edge joining this and this in the graph? In the original graph G. This is just a spanning tree, right? The white part. But
And we are
the original
solving
graph,
that even cycle problem.
no, we're not solving any problem.
This edge cannot be there, otherwise it would be at level 2 after going to 1.
Exactly, right? So I can't have an edge between a vertex of level 1 and a vertex of level 3, right? Because yeah, what's the problem with that? The problem is that then this vertex W is actually at a distance of 2 from the root. So I would actually have included it in the previous level. right? So this vertex would actually have been somewhere over here as W instead of being at level 3. So I can't have such edges. So
Oh, like in the original graph, it can exist, but while you're performing the breadth first search, you just ignore that. Isn't that possible?
but how do we ignore it? I mean, how is it possible to ignore it? Like, because we're taking all neighbors of neighbors and joining them, right?
Yeah,
So
okay, fine.
yeah.
Yeah.
So it's not possible for that to happen. Instead, so that is if if L1 plus 2 is less than equal to L2, then a vertex at level L1 cannot have an edge with a vertex at level L2. If you want to see it in a different way, it sort of violates triangle inequality because the distance between u and v is 1, the distance between u and w is 3, the distance between v and w is 1. So 1 plus 1 is less than 3 is a violation. This means that, okay, so reading this is a little painful. Okay, great. So this means that the remaining edges in the graph are only either between adjacent levels, so something of this sort, say this, and then this, etc., right? Or between the same level. So this is also okay. In fact, in this graph itself, we see that that this edge, and this edge, and even this edge is between the same level, and this edge is, and even this edge is between adjacent levels, but there are no other edges. And so this is always guaranteed in a breadth first search graph. Any questions?
It's clear.
Yeah. Okay. Great. And so using the idea of PFS, so I'm sort of giving it out that the idea is to use such a tree. Let's try this problem. So we have a simple finite graph on 2n plus 1 vertices and 3n plus 1 edges. And the task is to show that G has a cycle of even length. In fact, it's tight. Also show, I'll add it.
So here we again consider a BFS tree, and the key observation is that any more edge outside the tree must be between vertices of the same level.
Yes.
Because if they differ by one, then there will be a even cycle, and they cannot differ by two, because you told before.
Mm-hmm.
And after that, if we ignore the edges of the tree and only look at the other edges, then no two edges can have a common vertex, as otherwise we would again able to find a even cycle.
Okay. Okay.
So we are just done.
Yeah, that's one.
How did you finish after proving that the edges can be between the
I've not.
same
I've
level?
not. I've not done it. Let's all keep thinking. Yeah.
Okay.
I'll not move fast. So fast. So, okay, we have a BFS tree, the graph. And then we have more edges. Yeah. So let's assume the contrary, right? Suppose G doesn't have a graph of even length.
Uh, I think I got that. Shall I tell?
We'll wait for some more people to sort it. So okay, so remember that the edges outside the spanning tree join either vertices on the same level or on adjacent levels. So what happens if we join two vertices on adjacent levels? So what sort of a cycle do we observe? So let's join this and this. You know that the cycle is this, right? This is the cycle that we get on making our edge. And so the length of this is 4, which is not allowed. And let's try something else. Let's join this. And so the cycle formed is this. This has length 6, which is also not allowed. So in fact, for any two vertices on adjacent levels other than the vertices such that the edge between them is in the spanning tree, the cycle which is formed by adding that edge would have an even length. Why is that so?
Suppose let T be their topmost common level, like from which they are originating. Then
Okay.
both have length x and x till some point, and then one edge you added, and then other level edge in the other leaf. So it's 2x plus 2, which is even.
Yes, exactly. So let's say we join this, and so we sort of keep going up till we find a common edge. This vertex. It's also called the least common ancestor, but okay. Yeah, I mean, you can look at it as a vertex and then its descendants, etc. And so this vertex is the least common ancestor of these two vertices. Right? So if this is at level L and this is at level L plus 1, then we get a cycle of length 2L plus 2, which is a contradiction. So 2L plus 2. Actually, wait. Let me make a few copies of this so that we can reuse. Okay. Yeah, so if we have such an edge, and this is at level L plus 1, then we get a cycle of length 2L plus 2. In fact, it's not necessary that this least common ancestor will be on the top. We could have had an edge like this, where this is the least common ancestor. And so saying that this is D and this is D plus 1, and so we'll get a cycle of length 2D plus 2, which is also an even length cycle. And this is not allowed because we assume that G does not have a cycle of even length. So that this means that our remaining edges in the graph only connect vertices in adjacent levels, right? So we only need to be concerned about that. So such back edges don't exist. So different level, also called depth, different depth, um, 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 outside edge. I think they're called back edges. I'm not sure. So, or I think cross edges is a more apt term. Imply even cycle. Yeah. So now we have edges only on adjacent levels. And so these do not directly induce a graph of even length. So this doesn't do anything so far because the cycle induces odd length. So we need to think more. How many edges are there outside? So remember, G has 3n plus 1 edges and 2n plus 1 vertices. So this tree itself has 2n edges. And so we are left with n plus 1 cross edges. Right? And remember that there are 2n plus 1 vertices.
Oh, where did you? How it's two edges, by the way?
I'm sorry, I couldn't understand.
How is it two edges? Like, is it some defined thing?
There are 2n plus 1 vertices, right? So 2n edges. It's
Oh,
the
okay,
number of
okay,
edges
yeah.
is one less. Yeah.
Yeah.
It's a spanning tree. Yeah.
We
Yeah.
can
So
remark that any vertex, like let's say V, it cannot have two cross edges connected to it.
good. Yes. Why is that so?
Because suppose it had two vertices, two edges like Vx and Vy, then from X and Y their least common ancestor, let's say Z, then ZXVY is an even cycle.
Yeah. Exactly. Yeah. That's
And
perfect.
that will imply the bound.
Yes. Exactly. So consider a vertex and suppose it is joined to two vertices on its level. Right? So we have this cycle of length 5 and this smaller cycle of length 3. But what we can also do is have this larger cycle, which uses both these cross edges. So we can have this cycle, right? 1, 2. And this has length 6. So in general, for any vertex V, if we have two cross edges in here, and the least common ancestor of these is say W, then if this distance is D, then Vx, Vy, W, Vx is a 2D plus 2 length cycle, right? And that again contradicts what we've assumed. Is this clear? So uh, if a vertex uh, is incident to no incident on an edge. Wait. Yeah, I don't know. This would imply even cycle. Okay, so this cannot happen either. This means every vertex is incident on at most one cross edge. So how many cross edges then there can there be?
N.
N,
In
right?
total.
So exactly. So so there are 2n minus 1 vertices. And so basically these cross edges cannot have a common vertex. So if there are two cross edges that share a common vertex, then that directly implies that this vertex is incident on two cross edges. So what this means is that basically no two cross edges share share a vertex. So this implies that if there are k cross edges, then the set of vertices which are the endpoints of these cross edges are 2k in number, right? Because they're all distinct vertices. So this means we have so if there are 2n plus 1 vertices, we can have at most floor of 2n plus 1 over 2, which is n cross edges. Another way to see it is that if we had n plus 1 cross edges, then some two of them must share a vertex, because the double of n plus 1 is more than 2n plus 1. So it's like a pigeonhole principle thing going on, right? So if there were n plus 1 cross edges, then some two must share a vertex. And then we get this sort of a contradiction. But this is actually a contradiction because there were n plus 1 cross edges. In other terms, if there are n cross edges and the tree itself has 2n edges, then the whole graph has only 3n edges. But we assume that the graph has 3n plus 1 edges. So this is a contradiction. Yeah. Is this clear? We still remain to make the construction, but I'll leave that for homework.
I think that's just consider a star and pair things.
Uh,
I mean that
yes,
directly
I
gives.
got it. Yes, yes. Something like this. You mean this is what you mean, right?
Yeah.
Yeah. In fact, there are many such graphs. So not just these. So in fact, any such graph on 3n plus 1 vertices, if you try to construct, would always look like this. So it sort of looks like these triangles, and if we had centers on triangles, sorry, this is like an off discussion. Then if we put sort of like a weight on these center triangles and join two if they have a common vertex, then this forms a tree. In fact, we have to do something about the cut these vertices as well. So yeah, I mean it's not so direct, but yeah. So there's some such structure on these trees, which is quite interesting actually. So these are
Do
called.
you know some source where we can find more about this?
I don't know more sources. I just know it's called a cactus graph.
Okay.
because of how it sort of looks like. If you've played Mario, you might have seen these cactus-like enemies that look like balls stuck together. This sort of looks like that, but with triangles. Uh, anyway, tortoise. No, maybe it's a different enemy that you're talking about. Oh, tortoise, as in those Koopa shells, not those. So generally, they appear in like the desert levels in Mario. Uh, okay. Maybe okay. We've almost run out of time. I just wanted to let me just take 10 more minutes and just tell you what a depth first search is, and then you can try those problems on your own. I will post possibly many problems for you all to solve. So we saw breadth first search, and we also talk about what a DFS is, which is called a depth first search. So it's not similar to a breadth first search actually. The idea here is this. So maybe I should take the same graph. Oh, but erasing it is painful. Let me just remember what the graph is. Okay. I think it was this. Doesn't matter.
Is there like a nice way to represent graphs? Like, how did you remember such a big graph so easily?
I don't. I didn't. I think I made a mistake. Yeah, I think. No, there are no nice ways to remember it. I just sort of. I don't know. Yeah, I don't know if there are nice ways to remember graphs. Okay. So so in a depth first search, so remember the sort of the analogy I gave where you're on a city and you're trying to find a friend or something by going through these edges. So another way to do it is to go as deep as possible and then come back. So let me erase some edges so that it's a little more annoying. Uh, okay, so let's say we start with V. We pick any neighbor of it. Let's say we pick this, and then we pick any neighbor of that. So let's say we pick this, and then we pick this, right? And now we've run out of vertices to go to. Actually, let me take this edge as well. So we've run out of vertices to go to. So we go back to the. So we keep. Okay, so let me also draw one more. Yeah. So now we're here, and we go back because we can't proceed further. And from here itself, here as well, we can't proceed further. So we go back and then we pick this edge and then say this edge and then uh, this edge and then this edge and then this edge and then this edge. So it's like going as deep as possible instead of taking like a breadth first attitude. We commit to going as deep as possible, exploring more paths till we cannot, and then backtracking on the last possible city or a vertex here where we can actually proceed more and then proceeding through it. Yeah. So our graph here is like this. It has much longer paths, which makes sense, right? Because yeah, it's a depth first. Because we're going as deep as possible instead of the breadth strategy that we were applying earlier. And now again, not just the spanning tree, but there are interesting properties about the the tree itself, right? So or the back edge, the cross edges in the tree, in the graph. So the cross edges are uh, this, 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 and this. So let me draw it in another manner. Let's draw it like this. I know it's not a great example, but I hope. Okay. So the idea is this: can we have an edge like this?
No.
Why?
Because if it existed, then suppose you choose the rightmost path first, then let's say the second last edge is V2.
Vertex, you mean?
Yeah, sorry. The second last vertex is
V2.
V2. Then after searching the rightmost vertex to it, we should first search this edge and then go back.
Exactly.
Could
Yeah.
you repeat once again how is the algorithm performed?
Yes. So the algorithm is performed by starting. So we start at V and we pick any vertex not explored yet. So we pick this, and then we pick any neighbor of this, say W, that we've not seen yet, say this, uh, and then we pick any neighbor of X that we've not seen yet. We pick any vertex of Y of neighbor of Y we've not seen yet. And now if we cannot proceed further because there are no neighbors of Z that we've not seen yet, we go back to the last vertex that we came to that vertex from. So we came through Y, and so from Y we try to look at a new vertex, but we cannot do that. So we go back to X. From X we try to explore a new vertex, and so we have such a vertex T. From T we explore something new, and from A we explore something new. From B we explore something new. So I chose this. We could have chosen any one. So from C we explore D, and from D we explore E. And since we've explored everything, we are done.
Got it.
Yeah. So it's like a depth. So we go as deep as possible to search for to explore. Yeah. Okay. So let me draw a general depth first search tree. So a general tree might look like this. And the question is, can I have an edge like this if the white part was actually a depth first search tree? So for this graph, what we said was that I should not have deleted the other thing, but okay. For this graph, we said that such an edge is not possible because when we started exploring from V and then we backtracked here and then went here, right? But
How
if such an
just
edge
by
exists, yeah,
just by seeing the graph, how do you know what was the vertex where we started? Like if we started at
yeah,
some different vertex.
we don't. I'm just talking about this graph so far. Uh, this is exactly this graph, by the way. Yeah. So if this were the vertex that we backtrack to and this red edge were indeed present, then we would have gone here instead of going back and then exploring, right? Because we say that we keep going back till we find a vertex that we can explore further. So such an edge cannot exist here. So more generally, let this be our depth first search tree, and we draw it in such a way that the leftmost path is explored first. I mean, I can sort of adjust the drawing in such a way that that is true, right? I think that can answer your question. So I sort of just draw the graph in such a way that the leftmost part is what is discovered first.
No, I mean in this graph you have drawn, if we start from the bottom, the third vertex from bottom,
Can you
Then this
tell me
edge
the
can,
letter? Oh,
the
yes,
vertex
yeah. This
T,
is my
T.
true. This is, yeah. You're right. That I need to specify how I'm doing the depth first search. Yeah, but let's say this is the root, and uh, and and this is the graph obtained by some depth first search in the tree, right? Starting at this vertex. Yeah. So and so let's in fact fix the fact that we did this. This is how we explored the graph. Yeah. And let's come back to V for just for the sake of it. I know it complicates things, but yeah, I hope it was clear what the directions were. And so, can this red edge exist?
Yeah, now it can't.
Yeah, good. Why?
Because otherwise otherwise from the left vertex of that
This,
edge, we would have used it.
yes. So instead of going back here, we would have used this edge to explore. Yeah. So in more generally, what sort of edges don't exist in a DFS tree?
Could you repeat?
So can you sort of generalize it? So that is, let me draw
Uh,
another depth first search
if the
tree.
two vertices of the edge are not the root, like if any of the vertices is not the root, then
That's not true. So I can have an edge of this sort. This is okay.
or like from if they are originating from different edges from the root.
Yes, I understand what you mean. Yes. Yeah. So I can't have an edge like this. This is not allowed. I can't have an edge like this. I can't have an edge like this because the same logic applies. That we would have explored that edge, but we did not in the DFS tree. So there is some sort of a contradiction. The
So
point
here are
is,
we also fixing the route and the path because otherwise these edges might be there.
uh,
I think we can take any path and it'll still
no,
work.
because yeah, this white edges are edges formed by doing some DFS from the root. So then these edges cannot exist.
Like if you start from the leftmost bottom edge of the vertex of this graph.
I'm saying that this is the root, right? So
Oh,
how can
okay.
you
If you're
start from there? Yeah.
so if we fix the route and not the path, then are these edges? Then can we say that these edges are not there if we don't fix the path?
I mean, if it's a DFS tree, then there is some path on these, right? So I mean, this tree was formed by following some path, right?
So can it happen that for some path that these edge can be there, or
No, but these edges can't be there no matter what the path is, right?
and why is that so?
I mean, the same logic applies.
Mm.
So this tree was formed by following some path. In fact, a walk, I should say. This tree was formed by following some walk, right? So let that W be that walk corresponding to which this tree is obtained. Oops, sorry. So let W be the walk such which makes this tree, right? So then argue through W, right? Then I mean the same argument works. The walk doesn't exactly, I mean, as long as there exists a walk W which forms this tree, it doesn't matter, right?
I think a edge like a edge between two vertices can not be there if and only if like their nearest ancestor is just the root. Otherwise, I think
Yes.
it can be there.
Nearest ancestor is just the root is not true. Uh, in fact, there cannot be an edge between them if the nearest ancestor is not one of them. So I cannot this edge is also not okay, even though the least common ancestor is this vertex. The same problem arises. So the point is,
Oh, it can happen. Like, see, if we first go from left side. Oh, okay, sorry. Yeah, it will explore that. Yeah, never mind.
yeah. So this edge is also not okay. Yeah. So the point is that between if if there is a back edge, say u to v, so say uv. Okay, so let's sort of order so remember that we said that w is there exists some walk w such that this tree T is formed by following the walk W, right? These arrows that I made before. Oh, I think I deleted them. Okay, doesn't matter. So this walk is what I'm talking about. V to W, W to X, X to Y, Y to Z, Z back to Y, etc. Right? So let's say okay, so suppose UV is an edge in G, which is not an edge in T. Yeah. Then no, so suppose U appears before V in the walk. And so what can we say now? And suppose the least common ancestor common I'll sort of restate what this means. Ancestor of UV is W. So in particular, so let me pick a different U and V in this. So let's say I pick this as U and this as V. Yeah. And suppose this is an edge. Yeah. And so our least common ancestor is the root itself here. This is W. And so suppose we explode U before exploring V. Yeah. Now the point is that how was V explored? V was explored. So we actually came to U through W first, and then we must have gone back all the way to W and then explored V, right? Because W is the least common ancestor. That's the only way we could have formed such a tree. Because if the least common ancestor of U and V is W, then from W we must have explored U and then at some point come back and then went back to V, right? So, but the issue is that so we explored W U and then we went back to W and then explored V. But the point is that if UV is an edge, then okay, so if UV is an edge, then we would have explored V here, which is a contradiction. If W is not equal to U, if W is equal to U, we don't have a contradiction because then this edge doesn't really exist. Does that make sense?
Yeah.
So this means U must be the least common ancestor of u comma v. That is, u is in particular, u is an ancestor of v. U is an ancestor of v. Let me clarify what an ancestor means. An ancestor in this white portion, that is the tree itself. So it's literally like an ancestor. Like, so you have a person, and then you have its children, and then furthermore its children, etc. And so that directly makes it obvious what an ancestor means, right? So this means that the cross edges in the graph G must be between a vertex and its ancestor. So therefore, cross edges are between vertex and ancestor. This is true for DFS. Just for BFS, I'll remind that cross edges are between vertex and another vertex at level plus minus 1 or 0 from it. So BFS has edges between nearby vertices, and TFS has edges between vertices and ancestors. So yeah, so we've sort of gone a lot over time. I hope to do one question on DFS. You can sort of just try this later. So the idea is quite similar. In fact, so if G is a simple graph with degree at least 3 for each vertex, then G doesn't have a cycle of length 0. G has a cycle of length different from 0 mod 3. So it has quite, it sort of follows very directly from this DFS tree.
Also
idea.
in the DFS, once you drew, after finishing the search, you drew back it to V again. So in like general DFS, we don't do that for optimality, right?
Sorry, what do you mean?
Like
In the
after
tree
completing the
itself, I
search.
won't have more edges. Yeah. Yeah,
Yeah,
I
no,
mean,
I mean like
yeah. After completing the search, you don't need to come back to V. Yeah, that is
yeah.
true. Yeah. Okay.
So are there some problems where a normal tree argument would fail while BFS or DFS would work?
Yes. So this, for example, and there are more
Uh,
problems where we
but
use.
for this, even if the tree was not BFS, we could just argue that there cannot be edge between levels of different parity. And
That is true. Yes. Even so, we must take a BFS tree, right?
why, even if it is a normal tree, then we can still
Yeah,
fix a
sure.
root and
Yeah.
give levels.
Yes, that is true. Maybe if you try this problem, that would help. You can try this problem.
Okay.
There are problems where these facts are what are mainly important. Right? So these are like special spanning trees. In fact, we also saw special spanning tree in the first problem where we took the tree to be such that it uses all edges through a vertex. So although it doesn't have a name as such, but that was also helpful.
So will you be also sending some problem set?
Yes, yes. In fact, there are more problems here. So there are quite interesting problems. I hope to cover minimum spanning tree, but I didn't get the time to. So I'll put this in the problem set as well.
Okay,
This
so
is
could you
more.
also please put that mod 3 problem also?
Yeah, I'll put all these problems and more. I'll also put some problems that have more of an algorithmic flavor. It's up to you to do it. But yeah, but for but there will mainly be problems that are mathematical rather than algorithmic. Okay, questions?
What's your view on sufficient way to find paths and trails?
Yeah, an efficient way to find paths, the number of paths, right? Uh, I think it should be a a difficult problem, in fact. Yeah, I think the number of paths in a graph should not be an easy thing to find. Yeah.
And is there
And
any form algorithm for cycles or trails?
no, in fact, counting the number of cycles in a graph is also a difficult problem in general, or even trails. I think trails I'll have to think, but yeah, I don't think there are efficient algorithms for it either.
So there are no known algorithms as of now.
Yes, so unless there is something called, it's like P versus NP problem. If there's an efficient algorithm for these, then I think P would be equal to NP, which we believe is not true. It's like a complexity theory related stuff. Yeah, but yeah, we
So so this path is a complete NP complete problem.
uh, I mean, counting the number of paths, I think is in a class called sharp P. I think I'm not sure. I'll actually have to think about it. I think it's like a sharp P complete problem. But
What is the meaning of this?
uh, do we want to enter that discussion? We can take that discussion offline. It's a little
Okay.
tangent to what we've done. Yeah, but I'll tell you what it means. More questions?
And in the sense you're coming to India?
What?
No, offline in the sense you're coming to India or?
No, it means not on meets.
Ah, okay.
Yes. More questions? If none, then we can sort of stop.
Oh, do you have any Olympiad problems which have like BFS or DFS idea? Like which
Yes,
is
in
known?
fact, I think this is one, and there are even more. I have more. I don't think this uses BFS, DFS. This is just a tree in general. But yeah, there are problems which use. I There are at least two DFS problems and one BFS problem. Didn't get the PNP thing. Oh, I was just saying that the number of so counting the number of paths in a graph. So let me just write it. If there is an efficient way to true. Although I'll just try to sort of prove it formally before saying that I'm 100% sure that this if then statement that I made is correct.
But
Yeah.
in your class, you defined such problems as NP complete, right?
Uh, Actually, those are problems that are hard as well as an NP. So NP complete are problems necessarily in NP that are the hardest, right? Remember the definition. So I said that these NP complete problems are the hardest problems in NP, but there are problems outside NP as well.
What do you mean by hardest?
So that's exactly the term that I use in the class. So these are problems in NP such that if we can solve them efficiently, then we can solve everything in NP in P. That is, if we can solve that NP problem in P time, then P will be equal to NP.
So this paths is also then one of the hardest problems of NP, right?
No, but it is not in NP. So remember, NP complete was a problem inside NP, which is hardest. But there are problems outside it as well.
Oh,
So NP complete problem is a problem P which is in NP such that if we can solve P in poly time, then actually
so NP problems are those whose answer can be verified sufficiently, right? Efficiently.
efficiently, yes. But it is not obvious how to verify it. For example, if I sort of, it's not even obvious how to verify it if I sort of just give you the count of the path. It's not obvious how to check if this is correct. Oh yeah, you've linked this problem. In fact, this was in one of my problem sets. In fact, I've put a solution on the link that you've given. Yes, thanks for the problem. Yeah, so there are other problems that may be outside NP such that if you can solve them in polynomial time, then P equal to NP. They're called NP hard problems. So NP complete is really equal to NP intersection NP hard. That is problems which such that if we solve them, then P equal to NP, but they're also themselves in NP.
What's your user ID?
On AOPS?
Yeah.
Oh, it's it's biomathematics. Yes.
Okay.
Okay.
Thanks
More
for the
questions?
class.
Sure, no problem. Fine.
I'll stop recording then. Yeah.
Yes, yeah.